Let us start our first morning session today. I especially marked two remote talks for this morning because yesterday we had very good dinner, and I suppose that people should not speak immediately after that. But our speakers today are in Moscow. There is 6 hours time difference. So let us start the first talk. I'm glad to introduce you Professor Sergey Prants, my old friend. Now he is director of Pacific Oceanological Institute in Vladivostok, but now he is in Moscow, and he is corresponding member of Russian Academy of Sciences. So, Sergey, please, you can speak.
Well, thank you, Victor. Do you hear me?
Yes, we hear you. We
Yes.
hear.
Okay. Well. Hello to everybody. I think that you're in a good health after yesterday conference dinner. I wished to be there, but unfortunately, I'm in Moscow. First of all, my dear Victor, my congratulations to your anniversary. I wish you good health, good luck, good work. And so I start my talk devoted to chaotic atomic transport in optical lattices. Next slide, please. So you see that my talk will consist of 3 parts. First of all, I will talk about atomic transport in three-dimensional optical lattices. Then I go to the some analytical description of quantum description of chaotic transport in one-dimensional optical lattice. And then I'll be back to three-dimensional case. And now I'll start. Next slide. So optical lattices, they are created by using coherent counter-propagated laser beam that produce optical potential that can be employed to manipulate cold atoms loaded in the optical lattice from a magnet optical trap. There may be one-dimensional, two-dimensional, and three-dimensional optical lattices, depending on a number of counter-propagated laser beams. And you know that atoms in a standing light wave experience the action of the light-induced force and concentrate either new nodes or antinodes of the a light wave, depending on the size of the difference between the frequency of the optical transition of atom and the laser frequency. It's a so-called detuning. And optical lattices of various dimension and geometry have been experimentally implemented by adjusting the number of laser beams, their angles, their relative angles of propagation and phase, frequency and intensity. Changing the phase of the laser beams, it's possible to create optical lattice with different types of interference or without any interference. Next slide. And well isolated trapped cold atoms are ideal controllable candidates for studying chaos and quantum classical correspondence. The point is that most of the experimental and theoretical works have been carried out of resonance. And in this regime, spontaneous emission can be suppressed and simplifying implementation of experiments and calculations. But walking far from the resonance, one excludes from consideration a variety of interesting dynamic effects arising as a result of the interaction between internal and external atomic degrees of freedom. Even in an idealistic one-dimensional case, a number of dynamical effects has been theoretically and numerically found and studied. It's a chaotic Rabi oscillation, chaotic scattering of atoms, and dynamic fractals, Levy flights, and anomalous diffusion. Okay, next slide, please. New possibilities of horizontal and vertical transport of atoms over large distances are opened when working with three-dimensional lattices near the resonance. With now state-of-art experiments, the problem of control of motion of single atoms in such lattices becomes actual. We will consider theoretically and numerically the motion of cold atoms in a simplest three-dimensional optical lattice without interference. So such a lattice is created by superimposing three orthogonal laser staining waves. Well, the main task you can see here. Next slide. Well, now you see the nodal surface of the total electrical field strands to the left. It's very important that we will see that atomic behavior change cardinally when atoms cross or close these nodal surfaces. And to the right, you see the isosurfaces with different values of the electric field strands. Next slide. Okay, the phases of the laser beams are created in such a way that interference between counter-propagated laser beams is absent. Well, first of all, we will start in the semi-classical approximation and in the frame rotating with the laser frequency. You see the Hamiltonian, which consists of kinetic energy of atoms, the internal energy of atoms, and interaction of an atom with laser beams. So this approximation, I mean semi-classical approximation, is valid if atom momentum exceeds photon momentum and the atom field interaction energy is greater than the recoil energy, which atom gets after emitting or absorbing a photon. Next slide. From this Hamiltonian, the physics is essentially that of a single atom without any interference with neighbor atoms. More atoms would just increase the signal. So I will speak about one atom. Neglecting any relaxation and creating coherent evolution only, atomic dynamics with quantized internal degree of freedom and the classical translational degrees of freedoms can be described by the following Hamilton-Bloch equation. You see, it's 1, 2, 3, 4, 4, 4, 4, 9 equations. Well, the U and V are components of the atomic electric dipole moment. W is the population inversion, and P and X are momentum and coordinates. Next slide. Okay, you see this set has two control parameters. This one of them is the recoil energy, and another one is the detuning between the frequencies of atomic transition and laser frequency. And this set of equations have two integral of motions. You see the length of Bloch vector and the total energy. And the total energy consists of kinetic energy, optical potential, and internal energy. Next slide. Yes, possible regimes of atomic motion can be described by analyzing the total energy. And if the kinetic energy is not large enough to overcome the potential barrier, atom is trapped in a well of the optical potential. with the fallen transition with total energy less than zero. If the kinetic energy is greater than the interaction energy, atom performs a ballistic flight. And because the maximum value of the potential is 3, and we have that the ballistic mode of motion is relaxed at when h is greater than 3. Next slide. The most interesting mode of motion is expected to occur under the conditions when total energy between 0 and 3. In this case, the interaction energy in the course of time could be either larger or smaller, the atom kinetic energy, and the atom could be trapped in a well of the optical potential for a while, and then overcame the potential barrier to leave it. Therefore, atom is expected to have 3 possible modes of motion. Regular or chaotic oscillation in a well of the optical potential, the trapping mode, regular chaotic ballistic flies over the heels of the optical potential, the ballistic mode, and chaotic motion with intermittent trapping and flight, the wandering mode. And the regime of motion depends strongly on the initial condition and the values of the control parameters, which determine the value of the total energy H. Next slide. Okay. Well, next slide. Well, the system of equation, it's a 9-dimensional Hamiltonian dynamical systems with solutions in an abstract 5-dimensional phase space. And so it has a set of so-called Lyapunov exponent. And we will compute the maximal finite time Lyapunov exponent, which is computed as follows. Next slide. If the next slide. If the Lyapunov exponent is positive, we have chaos in a dynamical system. We see here the dependence of the Lyapunov exponent on the detuning. And you see that it is positive in a range with delta approximately between 0 and 1 in the positive direction and between 0.3 in the negative direction. So in this range of detuning, we expect chaotic motion. Next slide. So you see here momentum in time and xy projection of trajectory in the regular mode. It's a regular oscillation. Next slide. Here you see oscillation of the block variables, regular oscillation. Next slide. Well, a non-trivial translation motion, again, we expect when h is between 0 and 3. And to illustrate the chaotic regime of motion, we take the detuning equal to 0.25, in which Lyapunov exponent and 0.03. And next slide. And you see here, the dependence of the momentum on time is rather irregular, with fast and abrupt oscillations. And to the right, you see the trajectory projected on the xy plane. And you see oscillation in a well of the optical potential and then a long flight. Next slide. You see the oscillation of the component of the atomic electron dipole moment U to the left and atomic population inversion in the chaotic regime of motion to the right. You see that they are irregular. And the point is that this variable U is very important. And you see it jumps very irregularly and very abruptly. And the question is why? Next slide. The most, you see the light-inducing force change its value as the atom moves in the optical lattice. The most significant change in the momentum occur when atom approach nodal planes of the orthogonal standing waves, where the value of the electric field strength is equal to 0. And the light-induced force depends both on the spatial coordinates and on its internal atomic variable u. Since u is synchronized with the electric field strength component, it tends to 0 when atoms approach the nodal planes in any optical lattice. And it doesn't matter how large was the magnitude of u. Next slide. And you see, and then I go to the one-dimensional case to show you what's the basic reason of this behavior of the variable u and of the chaotic wandering of atom. You see here that a few years ago we have shown analytically that the gemplane behavior of the variable u can be described by the following stochastic map. You see here that um is the value of u just after crossing the m nodes in one-dimensional optical lasers, and phi m are random phases, and so on. And this stochastic map reflects very good statistics of atom, length of atomic flight, and many other parameters. Next slide. And the amplitude of jumps varies in a random-like manner. And here it's and this behavior follows from conservation of energy. That abrupt change of you mean change in the optical potential. That in turn causes change in atomic kinetic energy, resulting in phi change in the atom momentum. And so you see this change of reasons. Next slide. And you see how it looks in the one-dimensional lattice. You see abrupt jumps of u when it crosses each node of the standing wave. And this scheme, graphical representation of UM and arcsine UM maps. And you see if h between smaller than 1, you see that it's a trapping mode, and between them it's flight mode, and so on. Next slide. Okay, now I talked before this point. I talked about atomic dynamics in the semi-classical approximations. And now I will talk a little about fully quantum dynamics, when I will quantize not only internal degree of freedom of atom, but also translational degree of freedom of atom. And you see there's a full Hamiltonian in the momentum representation. The wave function looks here, and we can get the infinite set of equation for momentum probability amplitude. You see here, again, we have the same control parameters as in the semi-classical case, recoil energy and detuning. And next slide. The control parameters, the momentum probability. Next slide. And the Hamiltonian of the internal degrees of freedom, we will use a Drake state basis, can be written in the following form. And the probability amplitudes to find atom and point X can be obtained by a Fourier transform from the momentum representation. Next slide. And it's the equation, Schrödinger equation is a position representation. It can be written in the form of second order equation, number 16. Where C plus minus squared are probabilities to find atom in the Drake state potentials, respectively. We have two Drake state potentials. And the asymptotic relation solution has the form 17th. And you see that it's a very important formula that gives the probability to make a non-adiabatic transition from one of potential to another one. And the quantity omega d is the Doppler shift. Next slide. So we have three possibilities. When square detuning much larger than Doppler shift, the probability to make the transition is exponentially small, even when an atom crosses a node. The evolution of the atomic wave epoch is adiabatic. If square detuning much less than Doppler shift, the distance between the potential is small, and the atom changes the potential each time when crossing any node, with a probability close to unity. In the limit case data equals to 0, the atom moves in the resonant potential. And if the squared detuning is of the order of Doppler shift, the probability to change the potential or to remain in the same potential upon crossing a node are of the same order. In this regime, one may expect a proliferation of components of the atomic wave packet at the nodes and amplification of the wave function. Next slide. You see here illustration for all three possibilities. To the left, we see the atomic momentum versus time, momentum probability distribution of initially Gaussian atomic wave pocket versus time at the detuning when we have adiabatic motion, left slide, in the center motion at exact resonance, and to the right, motion with non-adiabatic transition. And the color codes the probability values. And you see, in the motion with not adiabatic transition, we see proliferations of wave packet. And it differs strongly on other cases. Next slide. The key result is the following. The amplitude of the U map is exactly the Ladin-Zener parameter k. If k is around 1, then the atomic variable xi um may take with the same probability practically any value from the range minus p2 to p2 to p2 just after crossing the Mond node. It means semi-classically that the momentum of a ballistic atom change chaotically upon crossing nodes of the standing wave. In accordance with the quantum formula, The corresponding atomic wave packet makes non-adiabatic transition when crossing the node and splits at each node. As a result, the wave packet of a single atom becomes so complex that it may be called a chaotic one in the sense that it's much more complicated than the wave packets propagating adiabatically. Thus, non-adiabatic wave chaos and semi-classical dynamical chaos occur in the same range of the control parameters and are specified by the same Landau-Zener parameter. In two limiting cases with k less than 1 and much greater than 1, both the semi-classical and quantized translation of ballistic motion are regular. Next slide. So, fully quantum equation of Mulkins now are numerically solved by the method of stochastic wave function. And in the numerical experiments, n-level atoms with a Gaussian initial distribution are prepared in the ground state, and the positions and momentum are calculated. The motion, a specific situation occurs in the range of those values of detuning when the interaction between the electronic and mechanical atomic degrees of freedom generates chaotic light dynamics, provided a splitting of atomic load. Next slide. You see here chaotic walking of atoms in one-dimensional optical lattices near the resonance, left slide, without spontaneous emission. No. Yes. And histograms of the distribution of atoms over position, left slide, and momenta. And it is spontaneous emission, but near the resonance. Next slide. But you see that the picture is different when we work in the chaotic regime. You see chaotic walking of atoms near the resonance with a count of spontaneous emission. Left is atoms over position and right momentum. Such atoms from the initial cloud, if we imagine that the axis of the standing waves is directed vertically, can move against the gravitational force in positive direction. You see here to the left, and the positive values of x means that the atoms move against gravitation. This can be used to realize a Lies-induced atomic elevator. Next slide. So Monte Carlo numerical simulation in one-dimensional lattice with a count of spontaneous emission has shown that, in fact, spontaneous emission facilitates observation of the chaotic walking in a real experiment because it increases the size of the initial cloud of atoms and even split an atomic cloud with an increase in the flight length of atoms in both directions. Next slide. And now let's return to 3D case and perform numerical experiments with a cloud of atoms with Gaussian initial distribution over position and momentum. And here we work in the semi-classical approximation. Now, a number of atoms are loaded in a trap, and 6 laser beams turn on to create a 3-dimensional standing wave. Next slide. Depending on the values of the detuning and the value of the Lyapunov exponent, we see different picture with distribution of large number of cold atoms. And you see here the distribution in the regular trapping mode at the red detuning. And projection of the 3-dimensional distribution to the planes all three planes are shown. And you see rather regular distribution in the closest cells of the optical potentials. Next slide. Now we work in the region of weak house at the blue detuning, and we see that atoms disperse in all the three dimensions as compared to the regular map. Next slide. And now the same but in strong chaotic region. And we see the dispersion of atom with very long flights. And this can be used to observe chaotic regime of motion with cold atom in three-dimensional optical lattice in real experiment. Next slide. So how to observe chaotic regime in real experiments? So we propose the following way to observe manifestation of chaos in real experiments with cold atom with common values of the spontaneous lifetime. The main point is to carry out a few sets of experiments with a large number of cold atoms and at two close values of the detuning. At the value of the detuning at which Lyapunov exponent is 0 or almost 0, and at the value of the detuning at which the Lyapunov exponent is positive. As our numerical experiments show, atoms are expected to be dispersed over larger distances in a three-dimensional optical lattice in the second chaotic case as compared to the first regular case. The contribution of quantum fluctuation to the total dispersion of atom is expected to be approximated the same at two close values of the detuning. Therefore, the observed difference between the two distributions of atomic clouds can be considered as a signature of deterministic chaos with cold atoms in three-dimensional optical lattices. Next slide. As to measuring the spatial extent of cold atomic cloud, an absorption imaging technique seems to be the most appropriate method providing information on the spatial parameters of atomic clouds and on the number of atoms. In this method, the atomic cloud is illuminated with near-resonance collimated laser beam just after the standing wave is turned off. Atoms scatter photons out of the beam, and the shadow cast by the atoms is registered by a CCD camera. The amount of light absorbed provides the optical density for each pixel and allows one to estimate the number of atoms. That's all. Thank you very much for your attention.